Now let's have a look at constraining our field values. Now you can well imagine that you create a type and the values that get added to that type need to be constrained in some way. Those values need to be constrained. Now I'm going to create a very simple type here called blood pressure. I think most of us understand blood pressure in as much as we express it usually in millimeters of mercury, and we would say normal blood pressure would be in the order of about 120/80. The first value, 120, refers to the systolic pressure. That's when the heart contracts and the blood gets pushed out of the heart, and there's this pressure wave of a high pressure value, and then the heart relaxes. It falls to more of a baseline pressure, and that would be the second lower value. So it's the higher peak value as the heart contracts and the lower value as the heart relaxes. So first one we call systolic, and the second one we call the diastolic. So 120/80 would be round about normal. And we can well imagine that we can't have a second value, the diastolic value, higher than the systolic value. That would just never work. We can also not have negative values. So that would be constraints on this type that we want to create. So let's have a look at this. Now you'll see immediately there's a lot more code here because that is what we need to constrain these values. And what we do inside of here, if you have a quick peek, is we create a function. And all of this combined is called it is at least part of the inner constructor of this type that we create. So let's use type. We don't want it to be immutable, so we just use the keyword type, blood pressure. Now we're going to have two field names here. We're going to call them systolic and diastolic. Never ever leave these as any. Be more specific than that. We don't want all sorts of type instability problems when we use functions with our user-defined types, etc. So we're going to say they're both 64-bit integer values. And then we're going to create this function. We also refer to it as blood pressure, same as the type. And it takes two arguments. And I'm just going to refer to them as S and D. Now, look at this. I'm going to use these, what I refer to as short circuit evaluations. This double and sign and these double straight downward lines. And I'm going to use them in 4 lines of code here. Let's look at the first one. It says, is S less than 0? So it's going to return a Boolean value for us, this S less than 0. If that returns a true, that is what this double and signs are. If that is true, then the second part will be evaluated. And it's a throw function of an argument error. And the argument error that we pass is some text, a string, and I've decided to write negative pressures are not allowed. So if the first value is less than 0, the systolic value is less than 0, I'm going to pass this argument to the screen, negative pressures are not allowed. And if S is less or equal to D, so another Boolean question I'm asking here, is the systolic pressure lower than the diastolic? If that returns a true, then we're going to throw another argument error and we say the systolic blood pressure must be higher than the diastolic blood pressure. You can well imagine that I could also have put a third one in here to say the D, the diastolic value, must also, if it evaluates to less than 0, we must also throw this argument. And then the following, I need them both to be integers. We cannot have floating point values. For that, I'm going to use this is a function, S, an integer. And now I use these double downward line signs, and that evaluates to an OR. So if this returns a true, is it an integer? The second part will not be evaluated. If it returns a false, if the systolic field value is a false, we will evaluate this second part, which will throw an error to say only integer values allowed. The same goes for the diastolic. If this returns a true, then the second part will not be evaluated. If it returns a false, then the second part will. And that is what we refer to as these shortcut evaluations. Then, if this executes, we need a new S and D. So a new blood pressure S, D for this function. And we end the function, this part of the inner constructor, and we end this type. So let's just run that code. And let's create an instance of our new blood pressure type, and we're going to pass 2 integers, no problem whatsoever, and we're going to call it BP_1, and we see we have a new instance of our blood pressure type holding the field values 120,80. So I'm not going to evaluate that code, but if we had BP_2 as our computer variable and we said blood pressure -1,90, it would have returned that error, the first one, negative pressures are not allowed. It's the first error that it's going to find in this inner constructor function of ours. If I were to say BP 80,120, we would have seen the argument error, load error, argument error. The systolic blood pressure must be higher than the diastolic blood pressure. And if either one of these are not an integer value, we would have seen only integer values allowed. So those would be the errors that we defined as part of the inner constructor of this type, constraining the types and values of the field that we can load. Now, I want to caution you about something. If we use an inner constructor with a parameterized type, we have to be very careful when we instantiate this type. So look at this type. I'm going to call it something else. We can't use the same type name again. Blood pressure parameterized. T must be a subset of the reals. And systolic and diastolic both of the same type. I use the same function for my part of my inner constructor. And I would evaluate this or run that code at least. And if I now try to create a computer variable called BP_3, an instance of my blood pressure parameterized type, 120,80, I'm going to get an error. And the error that I'm going to get is this, a load error, a method error. It cannot convert, has no method matching convert type blood pressure parameterized T being a subset of real to integer values. Now, that is very difficult to just read that and understand what the real error was. In Julia 0.5, that will be made slightly clearer, I believe, and we'll have a look when that is out. What you have to do, just to play it safe anyway, is when you do create an instance of this type that was constrained by an inner constructor and it is of a parameterized type, you have to specify the type of the 2 values that you are going to pass inside of these curly braces. So we're going to say BP_3 blood pressure parameterized. In curly braces, I'm going to pass 2 integer values and then pass those 2 integer values. And then we're going to get an instance of the blood pressure parameterized type. So just be slightly careful there. So the only difference between the two types that we've created here was that, first of all, it was not parameterized, so we needn't pass this value to the instantiation of that type. But if we do use a parameterized type, we do have to pass this type here when we instantiate the type. Now, there is a way to fix it, slightly convoluted, but I want to show it to you. I'm going to create just a shortened version. I'm going to call it blood pressure parameterized fixed, and all we're going to just do is systolic. Remember, it's still parameterized with the T there, subset of reals. We still have this as part of the inner constructor, this function of ours. So let's just evaluate that. There we go. Now, I can fix that so that I don't have to specify this inside of curly braces, the type of the field values that I am going to pass by doing the following. Bit convoluted, but follow and you'll see. We're going to say blood pressure parameterized fixed of this parameter T in curly braces, the 2 field values systolic T, diastolic of type T equals, again the type name, blood pressure parameterized fixed, is going to be of T, systolic diastolic. So this is an assignment. I'm assigning the right-hand side here. And I'm just saying that those 2 values will be of the type that you find from instantiating it, so that you don't have to specify it during the instantiation. So let's run that. And now I can instantiate this type without referring to the type. I only need to pass. It's now going to recognize that these are 2 integer values and pass that to the instantiation of this type for me. And I will have BP_4. It will recognize that they're 64-bit integers because of this assignment that I've done. And it will instantiate that type for me. And this is what we refer to as constructing, or at least using an outer constructor for our type, so that we needn't pass these values. They will be recognized from the values that are passed. Now you can well imagine that we can become much more specific if we want. You can really, it's really powerful what you can do with these user-defined types. So I'm going to do the following for my outer constructor. I'm going to say blood pressure parameterized fixed, this last one that we had. T must be a subset of the integers, and the value systolic, which is of same type, diastolic, which is of same type, must be a 64-bit float for those. So it's going to convert a 64-bit float. That would be the same as me having typed in there float 64, which I took away the need for here by this outer constructor. But now I'm going to say don't make them integers, even if I pass integer values, convert them to 64-bit floating values for me. So if I instantiate my type now, I get that they were changed to 64-bit integers. Now, that might at first notice seem a little bit strange because we had this outer constructor to say they were 64-bit integers, 64-bit floats, but we typed in two integers and it returned a 64-bit integer. So let's have a look. If we were to change them to 64-bit floating point values and we were to execute that, it's going to pick up that as well, to change them to 64-bit floating point values. Now, next up, we're going to have a look at slightly more complex parameters.